Hello there, and welcome to this channel. Tonight we drift into the depths of space, into where gravity becomes so regions intense that reality itself bends and warps beyond recognition. We're going to explore black holes, those mysterious cosmic giants that have captured human imagination for generations. Some are stellar graveyards, the collapsed remnants of massive stars. Others are supermassive behemoths lurking at the hearts of galaxies, millions or billions of times more massive than our sun. Each one is a doorway into physics so extreme that our everyday understanding of time and space simply breaks down. These cosmic secrets about us whole enig the birth and death of stars, the formation of galaxies, and the very of space fabric time itself. Tonight we'll journey through the event horizon and beyond, discovering how these invisible monsters shape the universe around them. We'll uncover the strange physics that governs their behavior and explore the profound questions they raise about the nature of reality. If you enjoy drifting off to cosmic wonders, feel free to like and subscribe or share your thoughts in the comments below. It helps others find their way to these nighttime explorations too, but for now, let these mysteries carry you into the quiet darkness of sleep. And if you're ready, let's begin our descent into the cosmic abyss. Black holes are not actually holes at all. Despite their name, black holes are not empty spaces or cosmic drains. They are regions of space-time where matter has collapsed into such incredible density that the gravitational field becomes overwhelming. Think of them as the most extreme objects in the universe where the normal rules of physics are pushed to their absolute limits. The term black hole was coined by physicist John Wheeler in 1967, but the concept itself dates back much earlier. These objects are invisible not because they are empty, but because their gravitational pull is so strong that not even light can escape once it crosses a certain boundary. The formation of stellar black holes begins with the death of massive stars. When a star at least 25 times the mass of our sun exhausts its nuclear fuel, it faces a catastrophic end. For millions of years, these stellar giants have maintained a delicate balance. Nuclear fusion in their cores creates outward pressure that fights against the inward pull of their own gravity. But when the fuel runs out, this balance collapses in spectacular fashion. The star's core implodes in less than a second, creating temperatures and pressures so extreme that protons and electrons are crushed together to form neutrons. If the core is massive enough, not even neutron degeneracy pressure can stop the collapse, and the matter continues to fall inward until it forms a black hole. The event horizon marks the point of no return around every black hole. This invisible boundary defines the region from which nothing can escape, not matter, not energy, not even information itself. The size of this boundary depends on the black hole's mass. For a black hole with the mass of our sun, the event horizon would have a radius of about 3 kilometers. For supermassive black holes, this boundary can stretch across billions of kilometers. What makes the event horizon so fascinating is that it represents a fundamental limit in our universe. Cross this line and you are forever separated from the rest of existence. Time behaves strangely near black to gravit holes, duational time dilation. Einstein's theory of general relativity tells us that time moves more slowly in stronger gravitational fields. Near a black hole, this effect becomes extreme. If you could watch someone falling toward a black hole from a safe distance, you would see them slow down as they approach the event horizon. their clocks would tick more and more slowly compared to yours. At the horizon itself, time would appear to stop completely from your perspective. The falling person, however, would experience time normally from their own reference frame, crossing finite the horizon in an amount of their own time. Supermassive black holes dwarf their stellar cousins by incomprehensible amounts. While stellar black holes typically contain a few times the mass of the Sun, supermassive black holes can contain millions or billions of solar masses. The supermassive black hole at the center of our own galaxy, known as Sagittarius A star, weighs about 4 million times as much as the Sun. Some of the largest known supermassive black holes exceed 20 billion solar masses. These cosmic giants didn't form from collapsing stars. Instead, they likely grew from smaller seed black holes that formed in the early universe, gradually accumulating mass by consuming gas, dust, and other black holes over billions of years. Every large galaxy appears to harbor a supermassive black hole at its center. This discovery has revolutionized our understanding of galaxy formation and evolution. The mass of these central black holes correlates remarkably well with the mass of the galaxy's central bulge of stars. This suggests a deep connection between the growth of galaxies and the growth of their central black holes. As gas falls toward the supermassive black hole, it forms an accretion disk that can outshine the entire galaxy. These active galactic nuclei can be seen across cosmic distances, serving as beacons that illuminate the early universe. Black holes can spin at incredible speeds, warping space-time around them. When matter falls into a black hole, it carries angular momentum with it. This causes the black hole to rotate, and some black holes spin at nearly the maximum rated by physics. A allow-spinning black hole drags space-time around with it in a phenomenon called frame dragging. Near a rapidly rotating black hole, space-time itself is twisted like honey around a spinning spoon. This rotation affects the shape of the event horizon and creates additional complexity in the physics of these objects. The interior of a black hole remains one of physics' greatest mysteries. Once matter crosses the event horizon, it falls toward the center where general relativity predicts it will encounter a singularity, a point of infinite density where the laws of physics break down. But many physicists suspect that quantum effects will intervene before true infinity is reached. The problem is that we cannot observe what happens inside a black hole. The event horizon acts as a one-way information barrier, preventing any signals from the interior from reaching the outside universe. This creates profound puzzles about the nature of information and the fundamental laws of physics. Hawking radiation suggests that black holes are not completely black after all. In the 1970s, Stephen Hawking made a startling discovery using quantum mechanics. He showed that the vacuum of space near a black hole's event horizon should produce pairs of virtual particles. Normally, these particle pairs annihilate each other almost instantly, but near the event horizon, one particle from the pair might fall into the black hole while the other escapes. The escaping particle becomes real Hawking radiation, carrying energy away from the black hole. This means that black holes should slowly evaporate over time, though for most black holes, this process would take longer than the current age of the universe. The temperature of Hawking radiation is inversely related to the black hole's mass. Smaller black holes are predicted to be hotter than larger ones. A black hole with the mass of the Sun would have a temperature of only about 60 nanokelvins, far colder than the cosmic microwave background radiation that fills space. But a black hole with the mass of a mountain would have a temperature of billions and of degrees would evaporate explosively in a fraction of a second. These primordial black holes, if they exist, could have formed in the early universe and might be detectable today through their gamma-ray emissions. Tidal forces near black holes can stretch objects into long, thin shapes. As you approach a black hole, the gravitational field becomes stronger at your feet than at your head, assuming you're falling feet first. This difference in gravitational strength creates tidal forces that stretch you vertically and compress you horizontally. For stellar mass black holes, these tidal forces become lethal long before you reach the event horizon in a process colorfully known as spaghettification. Supermassive black holes, however, have much gentler tidal gradients near their event horizons, meaning you could potentially cross the boundary intact. Black holes can act as gravitational lenses, bending light from objects behind them. Einstein's general relativity predicts that massive objects curve spacetime, and light follows these curves. When a black hole passes between Earth and a distant star, the black hole's gravity can focus the star's light like a lens, causing the star to appear brighter and sometimes creating multiple images. This gravitational lensing effect has been used to discover holes and study their properties. The distortion of light around black holes creates some of the most dramatic and beautiful phenomena in astronomy. Accretion disks around black holes can reach temperatures of millions of degrees. When matter spirals into a black hole, friction and magnetic forces in the accretion disk heat the gas to incredible temperatures. The inner regions of these disks glow with X-ray radiation, making them some of the brightest objects in the universe. The study of these X-ray emissions has provided much of our knowledge about black hole behavior. Jets of particles can also be launched from the vicinity of spinning black holes, shooting out at nearly the speed of light and extending for thousands of light years across space. The no-hair theorem suggests that black holes are remarkably simple objects. According to this principle, a black hole can be completely properties described by just three: its mass, its electric charge, and its angular momentum or spin. All other information about the matter that formed the black hole appears to be lost forever. This simplicity is both elegant and puzzling. It suggests that black holes are among the most fundamental objects in nature, yet it raises deep questions about what happens to information when it falls past the event horizon. Binary black hole systems can spiral together and merge in catastrophic collisions. When two black holes orbit each other, they gradually lose energy by emitting gravitational waves, ripples in spacetime itself. As they lose energy, their orbits decay and they spiral closer together. In the final moments before merger, they can orbit each other hundreds of times per second before colliding and forming a single, larger black hole. These mergers are among the most violent events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. The detection of gravitational waves has opened a new window into black hole physics. In 2015, the LIGO Observatory made the first direct detection of gravitational waves from a black hole merger. This discovery confirmed Einstein's predictions about the nature of spacetime and provided a completely new way to study black holes. Unlike light, gravitational waves can travel through matter without being absorbed or scattered, giving us an unobstructed view of some of the most extreme events in the cosmos. Black holes challenge our understanding of thermodynamics and information theory. The laws of thermodynamics seem to apply to black holes in strange ways. Black holes have entropy proportional to the area of their event horizons, not their volume. This suggests that the information content of a black hole is encoded on its surface rather than in its interior. But if black holes evaporate completely through Hawking radiation, what happens to the information that fell into them? This information paradox represents one of the deepest unsolved problems in theoretical physics. Some black holes may be connected to other regions of spacetime through wormholes. While highly speculative, solutions to Einstein's equations suggest that the interior of a black hole might connect to a white hole, a hypothetical object that XPD of consumingles matter and energy instead it. These Einstein-Rosen bridges or wormholes could potentially connect distant regions of our universe or even link to other universes entirely. However, such wormholes would likely be unstable and would collapse before anything could pass through them. Black holes may play a crucial role in seeding the formation of the first galaxies. In the early universe, the first black holes could have formed from the direct collapse of massive gas clouds or from the deaths of the first generation of stars. These primordial black holes would have served as gravitational anchors, pulling in surrounding matter and providing the seeds around which the first galaxies formed. The relationship between black holes and galaxies appears to be fundamental, with each influencing the other's growth and evolution throughout cosmic history. The centers of galaxies are far more dynamic places than they appear. While we often picture galaxy centers as quiet regions dominated by their supermassive black holes, the reality is much more turbulent. Gas streams spiral inward, heating to millions of degrees and creating brilliant accretion disks that can outshine billions of stars. Magnetic fields thread through this hot plasma, channeling some of the infalling matter into powerful jets that shoot out along the black hole's rotation axis. These jets can extend for hundreds of thousands of light years, carrying energy far beyond the galaxy itself and influencing star formation across vast regions of space. Active galactic nuclei represent some of the most energetic phenomena in the universe. When supermassive black holes actively consume large amounts of matter, they become visible across cosmic distances. Quasars, blazars, and radio galaxies are all manifestations of this feeding process. A single quasar can emit more energy than 1,000 galaxies combined, powered entirely by matter falling into a black hole no larger than our solar system. This incredible efficiency comes from the conversion of gravitational potential energy into electromagnetic radiation as matter accelerates toward the event horizon. Black holes can remain dormant for millions of years before awakening. Most supermassive black holes, including the one at the center of our galaxy, are currently quiet, consuming matter at a very slow rate. But when a star wanders too close, or when two galaxies merge and funnel gas toward the center, these sleeping giants can roar back to life. The awakening can be sudden and dramatic, transforming a peaceful galaxy center into one of the brightest objects in the observable universe. This cycle of dormancy and activity has shaped the evolution of galaxies throughout cosmic time. The environment around black holes creates natural particle accelerators. The strong magnetic fields and extreme velocities near black holes can particles to inert accelerate charges that dwarf anything achievable in human-made accelerators. These cosmic ray particles can reach energies trillions of times higher than the most experiments on powerful particle physics Earth. When these high-energy particles interact with matter or magnetic fields, they produce gamma rays, X-rays, and other forms of high-energy radiation that allow us to study the extreme physics occurring near black holes. Intermediate mass black holes occupy a mysterious middle ground. Between stellar mass black holes and supermassive ones lies a largely unexplored territory. These intermediate mass black holes, containing hundreds to hundreds of thousands of solar masses, are difficult to detect and poorly understood. They might form from the mergers of smaller black holes or from the direct collapse of massive star clusters. Finding and studying these objects could provide crucial insights into how supermassive black holes formed and grew in the early universe. The shadows of black holes can be directly observed by modern telescopes. The Event Horizon Telescope, a global network of radio dishes, has captured the first images of black hole shadows. These images show the dark silhouette of the event horizon surrounded by the bright glow of hot gas spiraling inward. The shadow appears larger than the actual event horizon due to gravitational lensing, which bends light rays around the black hole. These groundbreaking observations have confirmed many theoretical predictions about black hole behavior and opened up new possibilities for testing Einstein's theory in the strongest gravitational fields known. Time dilation near black holes creates profound paradoxes for observers. Imagine dropping a clock toward a black hole while watching from a safe distance. As the clock approaches the event horizon, you would see it ticking more and more slowly due to gravitational time dilation. From your perspective, the clock would appear to freeze at the horizon, its final tick stretched out over an infinite amount of your time. Yet from the clock's perspective, it passes through the event horizon and reaches the singularity in a finite amount of proper time, experiencing nothing unusual at the crossing. The information paradox represents one of physics' most challenging puzzles. When matter falls into a black hole, it carries information about its quantum state with it. According to quantum mechanics, information cannot be destroyed, only scrambled or transformed. But if black holes evaporate completely through Hawking radiation, where does this information go? Some physicists propose that the information is somehow encoded in the Hawking radiation itself, while others suggest that information might be preserved in the correlations between particles that fall in and those that escape. The resolution of this paradox may require a fundamental revision of our understanding of quantum mechanics or gravity. Primordial black holes could have formed in the first moments after the Big Bang. Unlike stellar black holes, which form from collapsing stars, primordial black holes could have formed directly from extremely dense regions in the early universe. These ancient objects might have a wide range of masses, from microscopic quantum black holes to intermediate mass ones. If they exist, primordial black holes could help explain dark matter, provide seeds for supermassive black hole formation, and offer a window into the conditions that existed in the first fraction of a second after the universe began. The ergosphere around spinning black holes offers unique possibilities. In the region just outside the event horizon of a rotating black hole lies the ergosphere, where space-time itself is dragged around by the black hole's spin. Within this region, it becomes impossible to remain stationary relative to distant observers. Objects are inevitably swept along in the direction of the black hole's rotation. Theoretically, the Penrose process could extract energy from a rotating black hole by dropping an object into the ergosphere, splitting it into two parts, and allowing one part to fall into the black hole while the other escapes with more energy than the original object possessed. Black hole mergers create ripples that travel across the entire universe. When two black holes spiral together and merge, they create gravitational waves that propagate outward at the speed of light. These waves stretch and compress space itself as they pass, though the effect is incredibly tiny. The merger events detected by LIGO involve black holes that are typically tens of times more massive than the Sun, located billions of light years away. Yet the gravitational waves from these distant catastrophes can still be measured on Earth using laser interferometers sensitive enough to detect changes in distance smaller than 1/10,000th the width of a proton. The firewall paradox challenges our understanding of what happens at the event horizon. Some physicists have proposed that instead of being an unremarkable boundary that you could cross pieced by a wallfully, the event horizon might be surrounded of high-energy radiation called a firewall. This firewall would incinerate anything attempting to cross the horizon, resolving certain paradoxes in black hole physics, but creating others. The firewall hypothesis remains highly controversial, with physicists divided on whether such extreme behavior at the horizon is necessary or even possible. Micro-black holes could potentially be created in particle accelerators. While extremely unlikely, some theories suggest that high-energy particle collisions might create tiny black holes that would evaporate almost instantly through Hawking radiation. These microscopic black holes would be far too small and short-lived to pose any danger, but their detection could provide valuable insights into quantum gravity and extra dimensions. The Large Hadron Collider at CERN has searched for evidence of such black hole production, though none has been found so far. Black holes might serve as cosmic recycling centers. While they consume matter and energy, black holes also return energy to their surroundings through Hawking radiation and the kinetic energy of their jets. Over extremely long timescales, a black hole will evaporate completely, returning all of its mass energy to the universe in the form of elementary particles and radiation. In this sense, black holes might be temporary storage facilities for matter and energy, holding it for eons before gradually releasing it back into space. This process operates on timescales so vast that it's difficult to comprehend, with stellar mass black holes taking longer than the current age of the universe to evaporate significantly. The holographic principle suggests that black holes encode information on their surfaces. This radical idea proposes that all the information about the three-dimensional volume of space surrounding a black hole can be encoded on the two-dimensional surface of its event horizon. If true, this principle would apply not just to black holes, but to any region of space, suggesting that our three-dimensional reality might be a holographic projection of information stored on a distant boundary. This concept has profound implications for our understanding of space, time, and the fundamental nature of reality itself. Naked singularities might exist without event horizons. While the cosmic censorship hypothesis suggests that all singularities should be hidden behind event horizons, some solutions to Einstein's equations allow for naked singularities, regions of infinite curvature that are directly visible to outside observers. If such objects exist, they would represent a complete breakdown of predictability in physics, as the chaotic behavior near the singularity could influence the rest of the universe in unpredictable ways. Most physicists hope that quantum effects or other unknown physics will prevent naked singularities from forming, preserving the cosmic censorship that keeps the universe's most extreme regions hidden from view. Black holes may exist in dimensions we cannot perceive. String theory suggests that our universe might contain more than the 3 spatial dimensions we experience. In these higher dimensional spaces, black holes could behave very differently from what we observe. They might be able to evaporate much more quickly, or their event horizons might have shapes that seem impossible in our 3-dimensional world. Some theories propose that microscopic black holes could be leaking gravitational effects into these extra dimensions, which might explain why gravity appears so much weaker than other fundamental forces. If this is true, then the black holes we study might be mere shadows of far stranger objects existing in realms beyond our perception. The relationship between black holes and entropy reveals deep connections to information theory. Jacob Bekenstein discovered that black holes have entropy proportional to the area of their event horizons, not their volume as we might expect. This means that a black hole's information capacity grows with the square of its size rather than with the cube. This relationship suggests that the fundamental information about everything that falls into a black hole is somehow encoded on its 2-dimensional surface, rather than distributed throughout its 3-dimensional interior. This discovery has revolutionized our understanding of how information and gravity level. Virtual interact at the most fundamental particles near black holes create a quantum foam of activity. Even in the apparent emptiness of space around a black hole, quantum mechanics tells us that particle pairs are constantly appearing and disappearing. Near the event horizon, this quantum activity becomes particularly important. The intense gravitational field can separate these virtual particle pairs before they annihilate each other, allowing one particle to escape while the other falls into the black hole. This process is thought to be the source of Hawking radiation, slowly aining energy from the black hole and causing it to shrink over vast periods of time. The mathematics of black holes connects to some of the most abstract areas of theoretical physics. The equations describing black hole behavior involve concepts from differential geometry, quantum field theory, and statistical mechanics. Solutions to Einstein's field equations reveal exotic space-time geometries where time and space can exchange roles, where geodesics spiral inward toward inevitable singularities, and where the normal rules of causality break down. These mathematical frameworks have led to insights that extend far beyond black hole physics, influencing our understanding of cosmology, particle physics, and the fundamental structure of reality. Rotating black holes create regions where space and time become twisted together. The Kerr metric describes how space-time behaves around a spinning black hole, revealing a complex geometry where the familiar min concepts of space and time become intergalled. Close to a rapidly spinning black hole, the dragging of spacetime becomes so severe that light itself gets caught up in the rotation. Photons trying to travel against the black hole's spin find themselves swept along despite moving at the speed of light. This frame-dragging effect demonstrates how mass and motion can literally reshape the fabric of reality. Black hole complementarity attempts to resolve fundamental paradoxes. This principle suggests that information falling into a black hole can be described in 2 complementary ways that never conflict for any single observer. From the outside, information appears to remain frozen at the event horizon and is eventually re-emitted in Hawking radiation. From the perspective of someone falling in, the information passes smoothly through the horizon and hits the singularity. These descriptions seem contradictory, but black hole complementarity proposes that no single observer can verify both simultaneously, preserving the consistency of physics, while allowing information to be both destroyed and preserved. The cosmic censorship hypothesis protects the universe from naked singularities. Roger Penrose proposed that nature has a built-in mechanism preventing singularities from being visible to outside observers. According to this hypothesis, whenever matter collapses to form a singularity, an event horizon must form to hide it from the rest of the universe. This cosmic censorship preserves the predictability of physics by ensuring that the chaotic, unpredictable behavior near singularities cannot influence the outside world. While widely accepted, this hypothesis remains unproven, and some exotic scenarios might allow naked singularities to form under extreme conditions. The interior geometry of black holes defies intuition in fundamental ways. Once inside the event horizon, the roles of space and time coordinates exchange in a sense. The radial direction toward the singularity becomes time-like, meaning that falling inward becomes as inevitable as moving forward in time. The singularity itself lies not at some distant location in space, but rather in the future of anyone who crosses the horizon. This geometric transformation means that escape from a black hole is not just practically impossible due to the required velocities, but is forbidden by the very structure of spacetime itself. Quantum effects near black holes might prevent singularities from forming. While classical general relativity predicts that matter falling into a black hole must eventually reach infinite density at a singularity, quantum mechanics might intervene before this extreme state is reached. Quantum gravity effects, which are not well understood, could cause the collapsing matter to bounce back or transform into something else entirely. Some theories suggest that the interior of what we call a black hole might actually contain a highly compressed but finite state of matter, avoiding the mathematical infinities that plague classical descriptions of singularities. The study of black holes has led to unexpected connections between gravity and thermodynamics. Black holes appear to have temperature and entropy. They can be in thermal equilibrium with their surroundings, and they obey laws analogous to the laws of thermodynamics. The first law relates changes in a black hole's mass to changes in its area and rotation. The second law states that the total area of black hole horizons can never decrease. These thermodynamic properties suggest deep connections between gravity, quantum mechanics, and statistical physics that we are only beginning to understand. Primordial black holes might have seeded the large-scale structure of the universe. If tiny black holes formed in the first moments after the Big Bang, they could have served as gravitational seeds around which matter later accumulated. These primordial density fluctuations might have grown over billions of years to become the galaxies and galaxy clusters we see today. The distribution of matter in the universe shows a web-like structure with vast voids separated by filaments of galaxies, and primordial black holes could have played a crucial role in shaping this cosmic architecture. The ergosphere of rotating black holes offers possibilities for energy extraction. Between the event horizon and the static limit of a spinning black hole lies a region called the ergosphere, where space-time is dragged around so violently that nothing can remain at rest. The Penrose process theoretically allows energy to be extracted from this region by sending in objects that split apart. with one piece falling into the black hole and the other escaping with more energy than the original object possessed. This mechanism could, in principle, allow advanced civilizations to harvest energy from rotating black holes, though the engineering challenges would be extraordinary. Traversable wormholes might exist as solutions to Einstein's equations. While the interiors of black holes seem to lead inevitably to singularities, some exotic solutions to general relativity describe space-time geometries that connect distant regions through tunnels or bridges. These Einstein-Rosen bridges could theoretically allow travel between different parts of the universe or even different universes entirely. However, keeping such wormholes open would likely require exotic matter with negative energy density, something that may not exist in nature. Even if traversable wormholes could exist, they would probably be highly unstable and would collapse before anything could pass through them. The quantum mechanics of black hole formation remains deeply mysterious. While we understand the classical process by which massive stars collapse to form black holes, the quantum mechanical description of this process raises profound questions. What happens to quantum information as it approaches the forming horizon? How do quantum correlations between particles inside and outside the black hole evolve? These questions touch on fundamental issues in quantum gravity and may require entirely new theoretical frameworks to resolve. Black holes might be connected to the arrow of time in our universe. The second law of thermodynamics, which describes the tendency of entropy to increase, gives our universe a clear direction in time. The formation and growth of black holes represents one of the most dramatic increases in entropy possible, as they have the highest entropy of any object for their size. Some physicists speculate that the prevalence of black holes in our universe might be connected to why time appears to flow in one direction rather than being symmetric between past and future. The holographic principle suggests that our three-dimensional reality might be an illusion. Inspired by black hole thermodynamics, physicists have proposed that all the information in a volume of space can be encoded on its two-dimensional boundary. This radical idea implies that our perceived three-dimensional world might actually be a holographic projection of information stored on a distant surface. If true, this principle would fundamentally change our understanding of space, dimensionality, and the nature of physical reality itself. Quantum entanglement might be preserved across black hole event horizons. Recent research suggests that particles falling into black holes might remain quantum mechanically entangled with particles outside, even after crossing the event horizon. This preservation of entanglement could provide a mechanism for information to eventually escape from black holes through correlations in Hawking radiation. The study of these quantum correlations has led to new insights connecting black hole physics to quantum information theory and the fundamental nature of space-time. The final fate of black holes depends on the ultimate destiny of the universe. If the universe continues to expand and cool, black holes will eventually become the dominant form of matter and energy. Over unimaginably long timescales, they will slowly evaporate through Hawking radiation until nothing remains but elementary particles and photons scattered across an ever-expanding cosmos. This heat death scenario represents one possible end to our universe, where even the most permanent seeming objects gradually fade away into the growing darkness of infinite space. Advanced civilizations might use black holes as ultimate sources of energy and computation. The extreme efficiency with which black holes convert matter into energy makes them attractive as power sources for hypothetical advanced technologies. The accretion process can convert up to 40% of infalling matter into energy, far exceeding the efficiency of nuclear fusion. Additionally, the extreme warping of space-time near black holes could theoretically be used for relativistic time effects, allowing computations to be performed at accelerated rates. Such possibilities remain in the realm of speculation, but they illustrate how black holes might serve not just as cosmic destroyers, but as tools for intelligence capable of harnessing their power. The study of black holes continues to challenge our deepest assumptions about the nature of reality. These objects exist at the intersection of general relativity and quantum mechanics, two theories that have never been successfully unified. Every new discovery about black holes seems to raise as many questions as it answers, pushing physicists to develop ever more sophisticated theories and mathematical tools. In probing these cosmic extremes, we are not just studying distant objects in space, but exploring the fundamental limits of physical law and the basic structure of existence itself. As we drift deeper into these cosmic mysteries, the strange physics of black holes reminds us that the universe operates on principles far more exotic and beautiful than our everyday experience suggests. In the warped space-time around these objects, time slows, space curves, and the very concepts of inside and outside lose their meaning. Yet from this apparent chaos emerges a deeper order, mathematical relationships that connect the physics of the very large to the quantum mechanics of the very small, suggesting hidden unities in the laws that govern all of reality. Black holes exist in a realm where the familiar becomes impossible and the impossible becomes routine. Near these objects, photons can orbit in circular paths, creating photon spheres where light travels in perfect circles around the gravitational well. These ghostly rings of trapped radiation exist just outside the event horizon, marking the boundary where light can still escape if pointed in exactly the right direction. From within this sphere, a photon aimed directly out hoverward might at the same distance forever, neither falling in nor flying away, suspended in an eternal dance with gravity. The mathematical description of black holes reveals symmetries that seem almost too elegant to be real. The Schwarzschild solution to Einstein's equations describes a perfectly spherical, non-rotating black hole with mathematical precision that has remained unchanged since 1916. Every such black hole of the same mass is identical to every other, regardless of what matter formed to bed it or how it came. This universality suggests that black holes represent a kind of fundamental state of matter, a cosmic attractor toward which sufficiently dense objects inevitably evolve. Stellar evolution provides the cosmic furnaces that forge black holes from ordinary matter. Throughout their lives, massive stars burn through successive layers of nuclear fuel, creating heavier and heavier elements in their cores. First, hydrogen fuses into helium, then helium into carbon and oxygen, continuing through silicon until iron begins to form. But iron cannot fuse to release energy, and when enough accumulates in the core, the star's fate is sealed. The core collapses in a catastrophic implosion that releases more energy in seconds than the star produced over millions of years of steady burning. The collapse process involves physics at the very limits of human understanding. As the stellar core implodes, electrons and protons are crushed together with such force that they merge into neutrons, releasing a flood of neutrinos that amounts of energy. If carry away enormous, the core exceeds about 3 solar masses. Not even neutron degeneracy pressure can halt the collapse. The matter continues to fall inward, compressing to densities that may exceed nuclear density by orders of magnitude, until general relativity takes over and an event horizon forms. Binary star systems can create some of the most energetic black hole formation events in the universe. When one star in a binary system evolves into a black hole while its companion remains a normal star, the black hole can begin stripping matter from its partner. This stolen gas spirals inward, heating to millions of degrees and emitting intense X-rays that make these systems visible across vast cosmic distances. Sometimes the mass transfer becomes unstable, leading to explosive outbursts that can briefly outshine entire galaxies. The accretion process around black holes converts gravitational potential energy into electromagnetic radiation with remarkable efficiency. As matter spirals inward through the accretion disk, magnetic fields threading through the hot plasma can channel some of the material into narrow jets that shoot outward at velocities approaching the speed of light. These jets can extend for millions of light years, carrying energy and momentum far beyond the black hole itself and influencing star formation throughout their host galaxies. Supermassive black holes appear to regulate the growth of their host galaxies through feedback mechanisms that operate across cosmic time. When these giants feed actively, their jets and radiation can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This creates a self-regulating cycle where the black hole grows by consuming gas, but its own activity eventually shuts off the supply of fuel. This delicate balance helps explain masses why galaxies correlate so closely with the masses of their central black holes. The formation of supermassive black holes in the early universe remains one of astronomy's greatest puzzles. Observations of quasars from when the universe was less than 1 billion years old reveal black holes already containing billions of solar masses. Growing such massive objects in so little time challenges our understanding of black hole physics. These ancient giants may have formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar formation process entirely and creating intermediate mass seed black holes that could grow rapidly in the dense environment of the young cosmos. Gravitational redshift provides a direct window into the extreme space-time curvature around black holes. Light climbing out of a gravitational well loses energy, causing its wavelength to stretch toward the red end of the spectrum. For light emitted near a black hole, this redshift can be enormous, with photons losing most of their energy by the time they reach distant observers. This effect allows astronomers to probe the space-time geometry close to event horizons, testing general relativity in its strongest possible regime. The concept of gravitational time dilation reveals how black holes affect the very flow of time itself. Clocks run slower in stronger gravitational fields, an effect that becomes extreme near black holes. A clock falling toward a black hole would appear to slow down dramatically as viewed by a distant observer, its ticking becoming more and more sluggish until it appears to freeze completely at the event horizon. Yet own from the clock experiencing perspective, it continues to tick normally, the of proper passage time, even as it crosses into the black hole's interior. Frame dragging effects around rotating black holes create regions where space-time itself participates in the rotation. Close to a spinning black hole, the fabric of space-time is twisted so severely that even light beams get caught up in the rotation. Objects trying to orbit in the opposite direction to the black hole's spin find themselves fighting against the current of dragged spacetime. This lens-thirring effect demonstrates how mass in motion can literally grip spacetime and drag it along, creating a cosmic whirlpool in the geometry of the universe. The E-arg itself, Osphere, represents a unique region where energy extraction from black holes becomes theoretically possible. Within this boundary, spacetime is dragged around so strongly that nothing can remain stationary relative to distant stars. The Penrose mechanism suggests that objects entering this region could potentially gain energy by splitting apart, with one fragment falling into the black hole while the other escapes with more energy than the original object possessed. This process could theoretically allow civilizations to extract rotational energy from spinning black holes, gradually slowing their rotation while harvesting enormous amounts of power. Quantum field theory in curved spacetime predicts that black holes should emit thermal radiation with temperatures inversely proportional to their masses. This Hawking radiation arises from quantum vacuum fluctuations near the event horizon, where virtual particle pairs can be separated by the intense gravitational field. The effect is extraordinarily weak for astrophysical black holes, with evaporation timescales that exceed the current age of the universe by countless orders of magnitude. Yet, for hypothetical microscopic black holes, the process could be rapid and violent, with tiny black holes exploding in bursts of high-energy particles and radiation. The information paradox emerges from the apparent conflict between quantum mechanics and general relativity at black hole event horizons. Quantum mechanics demands that information cannot be destroyed, only scrambled or transformed. But if black holes evaporate completely through Hawking radiation, what happens to the quantum information that fell past the event horizon? This puzzle has spawned numerous proposed solutions, from black hole complementarity to the holographic principle, each attempting to reconcile our understanding of quantum mechanics with the behavior of black holes. Black hole thermodynamics reveals deep connections between gravity, quantum mechanics, and information theory. The laws of black hole mechanics mirror the ordinary laws of thermodynamics, with black hole area playing the role of entropy and surface gravity corresponding to temperature. These relationships suggest that black holes are not just gravitational objects, but also thermodynamic systems with well-defined statistical mechanical properties. The discovery that black hole entropy is proportional to area rather than volume has profound implications for our understanding of how information is stored and processed in nature. The holographic principle proposes that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This radical idea emerged from black hole physics, where the entropy of a black hole depends on the area of its event horizon rather than its interior volume. If true, this principle would imply that our three-dimensional perception of reality might be a holographic projection of information stored on a distant two-dimensional surface. This concept has revolutionized theoretical physics and may hold the key to unifying quantum mechanics with general relativity. Wormhole solutions to Einstein's equations describe hypothetical tunnels through space-time that could connect distant regions of the universe. While closely related to black holes mathematically, traversable wormholes would require exotic matter with negative energy density to remain stable. Such matter violates the known energy conditions and may not exist in nature. even if traversable wormholes could be constructed, they would likely be subject to catastrophic instabilities that would cause them to collapse before anything could pass through them safely. The cosmic censorship hypothesis suggests that nature protects the universe from the chaotic unpredictability of naked singularities. This principle proposes that whenever matter collapses to form a singularity, an event horizon must form to hide the singularity from outside observers. Without cosmic censorship, the arbitrary and unpredictable behavior near singularities could influence the rest of the universe, destroying the deterministic nature of physical law. While widely believed by physicists, cosmic censorship remains an unproven hypothesis, and some exotic scenarios might allow naked singularities to form under extreme conditions. The interior geometry of black holes transforms the familiar concepts of space and time in fundamental ways. Inside the event horizon, the radial coordinate becomes time-like, while the time coordinate becomes space-like, meaning that falling toward the singularity becomes as inevitable as moving forward in time. The singularity itself lies not at some location in space, but rather in the future of anyone who crosses the horizon. This geometric transformation means that escape from a black hole is forbidden not just by the required velocities, but by the very structure of space-time itself. Quantum gravity effects might prevent the formation of true singularities inside black holes. While classical general relativity predicts that collapsing matter must reach infinite density, quantum mechanical effects that are not yet well understood might intervene before such extreme conditions are reached. Loop quantum gravity, string theory, and other approaches to quantum gravity suggest that the interior of black holes might contain exotic quantum states rather than classical singularities. These quantum effects could cause the collapsing matter to bounce back or transform into something entirely different. The study of black hole shadows using very long baseline interferometry has opened a new observational window into these extreme objects. The Event Horizon Telescope has captured images of the shadows cast by supermassive black holes, revealing the dark silhouette of the event horizon surrounded by the bright emission from hot accreting gas. These observations provide direct evidence for the existence of event horizons and allow detailed tests of general relativity in the strongest gravitational fields known to exist. Primordial black holes could have formed in the early universe through mechanisms very different from stellar collapse. Density fluctuations in the primordial plasma could have collapsed directly into black holes during the first moments after the Big Bang, creating objects with masses ranging from microscopic to stellar scales. These ancient black holes could help explain dark matter, provide seeds for supermassive black hole formation, and offer a unique probe of the conditions that existed in the very early universe. The merger of binary black holes creates some of the most violent events in the cosmos, briefly generating gravitational wave luminosities that exceed the electromagnetic output of all stars in the observable universe combined. As two black holes spiral together, they lose orbital energy to gravitational radiation, causing their orbits to decay and their orbital frequency to increase. In the final moments before merger, they can orbit each other hundreds of times per second before colliding and forming a single, more massive black hole surrounded by a highly distorted space-time geometry. Gravitational wave astronomy has revolutionized our ability to study black holes and test general relativity in the strong field regime. The detection of gravitational waves from black hole mergers has confirmed Einstein's predictions about the nature of space-time and provided unprecedented insights into the population and properties of black holes throughout the universe. Unlike electromagnetic radiation, gravitational waves propagate through matter without absorption or scattering, giving us an unobstructed view of some of the most extreme physical processes in nature structure. The mathematical of black hole space-times reveals hidden symmetries and geometric properties that continue to surprise researchers. The Kerr solution describing rotating black holes exhibits remarkable mathematical elegance, with the metric tensor taking forms that suggest deep connections to other areas of mathematics and physics. These geometric insights have led to advances not only in general relativity, but also in string theory, quantum field theory, and mathematical physics more broadly. Black holes may serve as natural laboratories for testing fundamental physics at energy scales and in gravitational field strengths that cannot be reproduced on Earth. The extreme conditions near black holes allow physicists to study the behavior of matter and energy in regimes where quantum mechanics, general relativity, and thermodynamics all play crucial roles simultaneously. These natural experiments continue to reveal new phenomena and push the boundaries of theoretical physics in directions that would be impossible to explore through terrestrial experiments alone. The relationship between black holes and the structure of space-time itself remains one of the deepest mysteries in modern physics. These objects represent regions where the familiar laws of physics break down and where our understanding of space, time, matter, and energy reaches its limits. Yet in studying them, we continue to uncover new principles and symmetries that govern the universe at its most fundamental level, suggesting that black holes may hold keys to understanding the ultimate nature of physical reality itself. As these cosmic mysteries continue to unfold before us, we find ourselves drawn ever deeper into questions that challenge our most basic assumptions about the nature of existence. In the strange realm of black hole physics, where time can stop and space can be torn, where information might be preserved or destroyed, where the very fabric of reality bends and warps beyond recognition, we encounter the universe at its most profound and mysterious. These objects stand as monuments to the incredible richness and complexity of the cosmos, reminding us that even in our age of advanced science and technology, the universe still holds secrets that can humble and inspire us with their beauty and strangeness. The gentle pull of these cosmic enigmas draws our thoughts inward, like matter spiraling slowly toward an event horizon. In contemplating these distant giants, we find ourselves at the edge of human knowledge, peering into depths that challenge our understanding while simultaneously revealing the elegant mathematical structures that underlie all of physical reality. As consciousness itself begins to dim like light red-shifted by gravity, these cosmic truths continue their eternal dance in the darkness, patient and timeless, waiting for minds yet to be born to unravel their remaining secrets. Black holes might exist in dimensions beyond our everyday experience. String theory and other advanced physics frameworks suggest that our universe could contain more than the three spatial dimensions we perceive. In these higher dimensional realms, black holes could behave in ways that seem impossible from our limited perspective. They might evaporate far more rapidly than predicted by standard physics, or their event horizons could take on shapes that defy our three-dimensional intuition. Some theories propose that what we observe as black holes might be mere shadows of far more complex objects existing in spaces our minds cannot fully visualize. The connection between black holes and the fundamental constants of nature reveals deep mysteries about why our universe has the precise properties it does. The formation of black holes depends critically on the relative strengths of gravity, electromagnetism, and the nuclear forces. If any of these forces were slightly different, black holes might not form at all, or they might dominate the universe so completely that stars and galaxies could never develop. This fine-tuning suggests either that we live in a specially selected universe among countless others, or that deeper principles we haven't discovered yet constrain these constants to their observed values. Virtual particles dancing near event horizons create a quantum foam of activity that challenges our understanding of empty space. Even in the apparent vacuum around a black hole, quantum mechanics tells us that particle pairs constantly appear and disappear in flests of feeding Burr-borrowed energy. Near the event horizon, the intense gravitational field can tear these virtual pairs apart before they can annihilate each other, transforming them from temporary fluctuations into real particles. This process slowly drains energy from the black hole while enriching the surrounding space with elementary particles and radiation. The thermodynamic behavior of black holes suggests they might be the universe's ultimate recycling systems. Over timescales so vast they dwarf the current age of the cosmos, every black hole will eventually return all of its mass energy to the universe through Hawking radiation. In this sense, black holes serve as temporary storage facilities for matter and energy, holding it for eons before gradually releasing it back into space as elementary particles. This cosmic recycling operates on schedules measured in goog, numbers so large that writing them out would require more atoms than exist in the observable universe. The study of black hole interiors pushes mathematics to its absolute limits. The equations describing the space-time geometry inside a black hole become increasingly exotic as one approaches the central singularity. Tidal forces grow without bound, time and space coordinates exchange roles, and the familiar concepts of distance and duration lose their meaning. Some mathematical solutions suggest that the interior might connect to other regions of spacetime or even to entirely separate universes, though these possibilities remain highly speculative and impossible to verify observationally. Quantum entanglement across event horizons creates paradoxes that shake the foundations of physics. When particles become entangled and one falls into a black hole while the other remains outside, their quantum connection appears to persist even after the horizon crossing. This preservation of entanglement across the boundary between inside and outside challenges our understanding of how information and causality work in extreme gravitational environments. The resolution of these paradoxes may require fundamental revisions to either quantum mechanics or general relativity. The formation of intermediate mass black holes remains shrouded in mystery. These objects, containing thousands to hundreds of thousands of solar masses, occupy a puzzling middle ground between stellar mass and supermassive black holes. They are too massive to form from single collapse events, but too small to be explained stellared by the same processes that create their supermassive cousins. Some might form through the collision and merger of many dense stellar smaller black holes in clusters, while others could result from the direct collapse of massive gas clouds in the early universe. Primordial black holes could serve as windows into the earliest moments of cosmic history. If tiny black holes formed from density fluctuations in the primordial universe, they would carry information about conditions that existed when the cosmos was less than a second old. The masses and distributions of these ancient objects would reflect the spectrum of density variations in the early universe, potentially revealing details about inflation, dark matter, and other fundamental aspects of cosmic evolution that cannot be studied through any other means. The ergosphere physics around rapidly spinning black holes creates opportunities for energy extraction that border on science fiction. Within this region where space-time is dragged around so violently that nothing can remain at rest, theoretical processes like the Penrose mechanism could allow advanced civilizations to extract rotational energy from black holes. By sending objects into the ergosphere and allowing them to split apart strategically, it might be possible to remove energy from the black hole's spin, gradually slowing its rotation while harvesting power equivalent to the annihilation of matter. Frame dragging effects demonstrate how mass in motion can grip the very fabric of reality. Around spinning black holes, space-time itself becomes twisted like thick fluid stirred by a cosmic spoon. This dragging of the space-time metric affects the motion of everything nearby, from individual photons to entire accretion disks. Light beams trying to travel against the black hole's rotation find themselves swept along despite moving at the ultimate speed limit, while objects attempting to orbit in the opposite direction must fight against the current of drag geometry. The mathematical elegance of black hole solutions to Einstein's equations reveals deep symmetries in the structure of spacetime. The Schwarzschild metric describing non-rotating black holes and the Kerr metric for spinning ones display mathematical properties that seem almost too beautiful to emerge from the complex tensor calculus of general relativity. These solutions possess hidden symmetries and geometric relationships that connect black hole physics to diverse areas of mathematics, from differential geometry to number theory. Hawking radiation temperature inversely relates to black hole mass in ways that seem to violate our intuitions about thermal systems. Smaller black holes are predicted to be hotter than larger ones, with microscopic black holes potentially reaching temperatures of billions of degrees Celsius, while supermassive black holes remain colder than the cosmic microwave background. This relationship means that as black holes evaporate through Hawking radiation, they become hotter and radiate faster, leading to a runaway process that ends in explosive evaporation for the smallest black holes. The holographic principle emerging from black hole physics suggests that reality itself might be fundamentally two-dimensional. This radical proposal holds that all the information in any three-dimensional volume can be encoded on its two-dimensional boundary. If true, our perception of living in three spatial dimensions might be an elaborate illusion, with the true degrees of freedom of the universe residing on distant surfaces. This holographic duality has profound implications for quantum gravity and our understanding of the nature of space itself. Gravitational lensing around black holes creates optical illusions on cosmic scales. The intense curvature of space-time near these objects bends light rays like a funhouse mirror, creating multiple images of background objects, stretching some features while compressing others, and sometimes creating complete rings of distorted light called Einstein rings. These lensing effects can magnify distant galaxies, allowing astronomers to study objects that would otherwise be too faint to observe, while also providing precise tests of general relativity. The cosmic censorship hypothesis protects the universe from the unpredictable chaos that naked singularities would unleash. This principle suggests that nature has built-in mechanisms preventing singularities from being visible to outside observers. If cosmic censorship fails and naked singularities can form, the arbitrary and uncontrollable physics near these regions of infinite curvature could influence the rest of space-time in ways that would destroy the predictable, deterministic nature of physical law. The preservation of causality and determinism throughout the universe may depend on this cosmic modesty principle. Binary black hole spirals create gravitational symphonies that ripple across the cosmos at the speed of light. As these pairs spiral together over millions of years, they emit gravitational waves that carry away orbital energy, causing the black holes to draw closer and orbit faster. In the final moments before merger, they can complete hundreds of orbits per second, while generating gravitational wave luminosities that briefly exceed the electromagnetic output of all stars in the observable universe combined. The detection of gravitational waves has transformed black holes from theoretical curiosities into directly observable phenomena. Advanced LIGO and Virgo detectors can measure spacetime distortions smaller than 1/10,000th the width of a proton, allowing them to record the gravitational signatures of black hole mergers occurring billions of light years away. These detections have confirmed Einstein's predictions about the behavior of strong gravitational fields and opened an entirely new window for exploring the universe. Accretion disk physics around black holes creates some of the most efficient energy conversion processes in nature. As matter spirals inward through these disks, gravitational potential energy is converted to heat and radiation, with efficiencies that can exceed 40% for rapidly spinning black holes. This process can convert rest mass to energy far more efficiently than nuclear fusion, making actively feeding black holes among the brightest objects in the universe despite their relatively compact sizes. Magnetic field lines threading through black hole accretion disks can launch jets of plasma that extend across galactic distances. These relativistic jets, powered by the rotation of the black hole and the magnetic energy stored in the surrounding plasma, can carry matter and energy millions of light years from their sources. The jets interact with the intergalactic medium, creating enormous radio-emitting lobes that can influence star formation throughout entire galaxy clusters. Active galactic nuclei powered by supermassive black holes can outshine their entire host galaxies. When these cosmic giants feed actively on surrounding matter, the energy released from their accretion processes can exceed the combined light output of hundreds of billions of stars. These quasars and other active nuclei serve as cosmic beacons, visible across most of the observable universe and providing insights into conditions in the early cosmos when galaxy formation was at its peak. The relationship between supermassive black holes and their host galaxies reveals a cosmic symbiosis that operates across billions of years. The masses of central black holes correlate remarkably well with the properties of their surrounding stellar bulges, suggesting that galaxy evolution and black hole growth are intimately linked. Feedback from active black holes can regulate star formation throughout their host galaxies, while galaxy mergers can funnel gas toward central black holes, triggering periods of rapid growth and intense activity. Tidal disruption events occur when stars venture too close to supermassive black holes and are torn apart by gravitational forces. As a star approaches within the tidal radius, differential gravity stretches it beyond its ability to hold together. Part of the stellar material falls into the black hole, creating a bright flare that can outshine the entire galaxy for months or years, while the remainder is ejected into space at high velocities. These dramatic events provide opportunities to study otherwise dormant supermassive black holes. The event horizon represents a fundamental boundary in space-time beyond which information cannot escape to the outside universe. This one-way membrane allows matter and energy to fall inward but prevents any signals from returning. The horizon's size scales directly with the black hole's mass, ranging from a few kilometers for stellar mass black holes to billions of kilometers for the most massive supermassive black holes. Despite being invisible, the horizon's effects on nearby matter and light reveal its presence. Space-time curvature near black holes becomes so extreme that it can trap light in circular orbits. At a distance of 1.5 times the event horizon radius, photons can orbit the black hole in perfect circles, creating a photon sphere where light travels in closed loops. Any photon orbiting closer than this distance will spiral inward and be consumed, while those farther out can escape to infinity. This photon sphere represents the innermost boundary from which light can still reach distant observers. The interior space-time of black holes transforms familiar concepts of space and time in ways that challenge human intuition. Inside the event horizon, the radial direction toward the singularity becomes time-like, meaning that falling inward becomes as inevitable as moving forward through time. The singularity itself exists not at some location in space, but rather in the future of anyone who crosses the horizon. This geometric transformation makes escape impossible not due to insufficient velocity, but due to the fundamental structure of space-time itself. Quantum field theory in the curved space-time around black holes predicts phenomena that have no analogs in flat space. The intense gravitational fields can create particle pairs from vacuum fluctuations, separate virtual particles before they can annihilate, and cause accelerated observers to perceive radiation where inertial observers see only empty space. These effects demonstrate how gravity and quantum mechanics interweave in ways that continue to challenge theoretical physicists. The firewall paradox proposes that black hole event horizons might be surrounded by walls of high-energy radiation, rather than being the smooth, unremarkable boundaries predicted by classical general relativity. This controversial hypothesis attempts to resolve certain information paradoxes by suggesting that anything attempting to cross the horizon would be incinerated by intense radiation. While highly debated, the firewall proposal highlights deep tensions between different principles of physics that remain unresolved. Black hole complementarity suggests that the same physical process can be described in seemingly contradictory ways that never conflict for any single observer. From outside the black hole, infalling information appears to remain at the horizon and eventually re-emerge in Hawking radiation. From the perspective of someone falling in, the information passes smoothly through the horizon and hits the singularity. These descriptions seem incompatible, but complementarity proposes that no observer can verify both simultaneously, preserving consistency. The ADS-CFT correspondence connects black hole physics in anti-de Sitter spacetime to quantum field theories living on the boundary of that space. This remarkable duality suggests that gravitational physics in the bulk spacetime is equivalent to non-gravitational quantum field theory on the boundary, providing a concrete realization of the holographic principle. While highly mathematical and abstract, this correspondence has led to new insights into both quantum gravity and strongly coupled quantum field theories. Traversable wormholes would require exotic matter with negative energy density to remain stable against collapse. While Einstein's equations admit solutions describing space-time tunnels connecting regions, keeping distant such passages open would likely require matter that violates the energy conditions obeyed by all known forms of matter and energy. Even if exotic matter could exist, quantum effects would probably destabilize any macroscopic wormhole, causing it to collapse before anything could travel through. The study of black hole microstates attempts to provide a statistical mechanical foundation for black hole thermodynamics. String theory and other quantum gravity approaches suggest that black holes might be composed of enormous numbers of microscopic quantum states, with the black hole's entropy arising from the number of ways these microstates can be arranged. Understanding these microscopic degrees of freedom could resolve paradoxes about information loss and provide a complete quantum description of black hole physics. Primordial black holes spanning an enormous range of masses could have formed through various mechanisms in the early universe. Density fluctuations, phase transitions, cosmic string collapse, and other exotic processes in the primordial cosmos might have created black holes with masses ranging from the Planck scale to many solar masses. These ancient objects could constitute part of dark matter, serve as seeds for supermassive black hole formation, and provide unique probes of early universe physics. The cosmic microwave background might preserve subtle imprints of primordial black holes that evaporated in the early universe through Hawking radiation. As these ancient black holes evaporated, they would have deposited energy into the surrounding plasma, potentially leaving detectable signatures in the temperature fluctuations of the cosmic background radiation. Future observations of these signals subtle could reveal holes that existed properties of the population and in the first moments after the Big Bang. Loop quantum gravity suggests that the interior of black holes might contain quantum bounces rather than classical singularities. In this approach to quantum gravity, the extreme density and curvature near the center of a black hole could trigger quantum geometric effects that halt the collapse and cause the matter to rebound. This quantum bounce might create a white hole on the other side, though such exotic objects would likely be hidden behind event horizons and remain unobservable from the outside. The black hole information paradox has inspired numerous proposed resolutions that challenge our fundamental understanding of quantum mechanics and gravity. From black hole complementarity to firewalls, from holographic encoding to information reflection, each proposed solution requires abandoning or modifying cherished principles of physics. The ultimate resolution may require a complete revolution in our understanding of space, time, quantum mechanics, or gravity, comparable to the conceptual upheavals that accompanied the development of relativity and quantum theory. Quantum error correction codes emerging from black hole physics suggest deep connections between information theory and space-time geometry. The holographic principle implies that quantum information stored in the interior of a region must be recoverable from its boundary, even in the presence of noise and decoherence. The mathematical structures that enable this error correction bear striking resemblances to the geometric properties of curved spacetime, hinting at profound relationships between information and gravity. The complexity of quantum states associated with black holes grows linearly with time for exponentially long periods. This quantum complexity, which measures how difficult it would be to construct the black hole's quantum state from simple operations, continues increasing long after the black hole has reached thermal equilibrium. This behavior suggests that black hole interiors might serve as natural computers, processing implications for our understanding of computational quantum information in ways that could have complexity and the nature of time. As our journey through these cosmic mysteries draws toward its quiet conclusion, we find ourselves contemplating objects that exist at the very edge of human comprehension. Black holes stand as monuments to the incredible richness and strangeness of our universe, places where the familiar laws of physics are stretched to their breaking point and beyond. In their silent depths, they hold secrets about the nature of space and time, matter and energy, information and reality itself. These gravitational titans continue their eternal dance in the darkness of space, patient and timeless, waiting for future generations of scientists to unlock their remaining mysteries. As we drift toward sleep, we can let our minds wander through the warped space-time around these cosmic giants, carried along like photons following the curved geodesics of general relativity toward regions where our current understanding fades into beautiful uncertainty. In the gentle embrace of approaching dreams, the mathematical elegance of black hole physics continues to unfold in dimensions beyond our everyday perception. The universe reveals itself as far stranger and more wonderful than our ancestors could have imagined, full of objects that challenge our deepest assumptions about the nature of existence, while simultaneously displaying an underlying unity that connects the quantum realm to the cosmic scale. The mysteries of black holes remind us that even in our age of advanced science and sophisticated instruments, the cosmos still holds secrets that can humble and inspire us with their profound beauty. As consciousness itself begins to dim like starlight redshifted by gravity, these cosmic truths persist in their timeless dance, waiting patiently for minds yet to be born to continue the endless quest for understanding in this strange and magnificent universe we call home. The relationship between black holes and the arrow of time reveals connections to the deepest mysteries of temporal flow. In our universe, time appears to have a preferred direction, flowing inexorably from past to future. Black holes participate in this cosmic asymmetry in profound ways. Their formation represents an irreversible increase in entropy, as matter transitions from organized stellar structures to the maximum entropy state of a black hole. The process of black hole evaporation through Hawking radiation also respects this temporal arrow, proceeding slowly forward through cosmic time rather than reversing spontaneously. Near black holes, the warping of space-time creates regions where the flow of time becomes increasingly alien to our everyday experience. Close to the event horizon, time dilation becomes so extreme that processes, which take seconds for an infalling observer, stretch across eons as viewed from a safe distance. This temporal stretching creates a kind of cosmic archaeology where light emitted just before horizon crossing becomes increasingly redshifted and time-dilated, preserving a frozen image of the final moments before disappearance. The study of black hole thermodynamics has revealed surprising parallels between gravitational physics and the behavior of ordinary thermal systems. Black holes possess temperature, entropy, and even participate in phase transitions under certain conditions. Their entropy, proportional to surface area rather than volume, suggests that the information content of these objects is fundamentally two-dimensional despite their three-dimensional appearance. This discovery has revolutionized our understanding of how information is stored and processed in gravitational systems. Quantum fluctuations in the vacuum near black holes create a rich tapestry of virtual particle activity. The intense curvature of spacetime amplifies these quantum effects, potentially transforming virtual particles into real ones through processes that have no analog in flat spacetime. The inter-near play between quantum mechanics and curved geometry event horizons continues to yield insights into the fundamental nature of both theories, pushing physicists toward new frameworks that might eventually unite these seemingly incompatible descriptions of reality. The mathematical structure underlying black hole physics displays an elegance that suggests deep truths about the architecture of the universe. The differential equations describing curved spacetime around these objects exhibit symmetries and conservation laws that mirror patterns found throughout theoretical physics. These geometric relationships hint at underlying principles that govern not only gravitational phenomena, but potentially all fundamental interactions in nature. Black holes serve as natural laboratories where the most extreme conditions in the universe unfold according to mathematical laws of breathtaking precision. In these cosmic furnaces, matter is compressed to densities that exceed nuclear values. Spacetime is curved beyond the limits of human visualization, and time itself becomes malleable. The physics operating in these environments pushes our theories to their absolute limits, often revealing new phenomena that could never be studied under terrestrial conditions. The formation mechanisms of supermassive black holes in the early universe remain among the most challenging puzzles in modern astrophysics. These objects appear in observations of the distant cosmos already containing billions of solar masses, when the universe was less than a tenth of its current age. The rapid growth required to reach such enormous sizes in such a short time challenges our understanding of accretion physics and suggests that exotic formation pathways might have operated in the dense, chaotic environment of the early cosmos. Intermediate mass black holes occupy a mysterious realm between their stellar and supermassive cousins. These elusive objects, if they exist in significant numbers, could provide crucial links in understanding how black holes grow and evolve over cosmic time. Their formation mechanisms remain unclear, potentially involving the collision and merger of many smaller black holes in dense stellar environments, or perhaps arising from the direct collapse of massive gas clouds under special conditions. The ergosphere surrounding rapidly spinning black holes creates a region where the very concept of remaining stationary loses its meaning. Within this boundary, spacetime itself is dragged around so violently that even light cannot resist the rotational flow. Objects entering this region find themselves inevitably swept along in the black hole's rotation, unable to hover at fixed positions relative to distant stars. This frame-dragging effect demonstrates how mass in motion can literally grip the fabric of space-time and force it to participate in the rotation. Gravitational waves from black hole mergers carry information about the properties and behavior of space-time in the most extreme environments known. These ripples in the fabric of reality propagate outward at light speed, carrying encoded details about the masses, spins, and orbital dynamics of their sources. The detection of these waves has confirmed theoretical predictions about the nature of gravity, while opening an entirely new observational window into phenomena that were previously accessible only through mathematical theory. The cosmic web of large-scale structure might owe its existence partially to the gravitational influence of primordial black holes. If these ancient objects formed in the early universe, they could have served as gravitational seeds around which matter began to accumulate. The complex filamentary structure of galaxies and galaxy clusters that we observe today might trace back to the distribution of these primordial density fluctuations, making black holes fundamental architects of cosmic structure. Magnetic fields threading through black hole accretion disks can tap into the rotational energy of spinning black holes to power some of the most energetic phenomena in the universe. The Blandford-Znajek mechanism describes how magnetic field lines can extract energy from the ergosphere, launching jets of relativistic plasma that extend far beyond the black hole itself. These jets can influence star formation and galaxy evolution across vast regions of space, demonstrating how black holes can affect their cosmic neighborhoods on scales millions of times larger than their event horizons. The interior space-time geometry of black holes might contain structures far more complex than the simple singularities predicted by classical general relativity. Quantum effects, extra dimensions, or exotic matter states could create intricate inner landscapes that bear no resemblance to our three-dimensional intuitions. The true nature of black hole interiors remains hidden behind event horizons, protected by cosmic censorship from direct observation, and accessible only through theoretical speculation and mathematical exploration. Tidal forces near black holes demonstrate how differential gravity can reshape matter in fundamental ways. As objects approach these gravitational giants, the difference in gravitational strength between their near and far sides creates stretching forces that can overcome all other physical interactions. For stellar mass black holes, these tidal effects become lethal long before the event horizon is reached, while supermassive black holes allow objects to cross their horizons relatively intact before tidal forces become overwhelming deeper in the gravitational well. The photon sphere around black holes represents a unique region where light can orbit in perfect circles. At precisely 1.5 times the event horizon radius, photons can follow closed circular paths around the black hole, neither falling inward nor escaping to infinity. This unstable equilibrium creates a boundary between the regions where light can escape and where it must inevitably be consumed. The photon sphere serves as the innermost limit from which electromagnetic radiation can still reach distant observers. Hawking radiation emerges from quantum field theory calculations in curved spacetime, predicting that black holes should slowly evaporate by emitting thermal radiation. The temperature of this radiation scales inversely with the black hole's mass, making smaller black holes hotter and causing them to evaporate faster as they shrink. This creates a runaway process for the smallest black holes, which would become increasingly hot and radiate increasingly rapidly until they disappear in final bursts of high-energy particles and gamma rays. The holographic principle suggests that the three-dimensional physics occurring in any region of space can be encoded on the two-dimensional boundary of that region. This radical proposal emerged from black hole thermodynamics, where the entropy of a black hole depends on the surface area rather than its volume. Area. If true, this principle would imply that our perception of living in three spatial dimensions might be a kind of holographic illusion, with the fundamental degrees of freedom residing on distant boundaries. Wormhole solutions to Einstein's equations describe hypothetical tunnels through space-time that could connect widely separated regions of the universe. While mathematically possible, these Einstein-Rosen bridges would likely require exotic forms of matter with negative energy density to remain stable. Even if such matter could exist, quantum effects would probably cause macroscopic wormholes to collapse catastrophically before anything could traverse them safely. The cosmic censorship hypothesis protects the predictability of physics by ensuring that singularities remain hidden behind event horizons. If naked singularities could form and be visible to outside observers, their chaotic and unpredictable behavior could influence the rest of space-time in ways that would destroy the deterministic nature of physical law. The universe appears to have built-in mechanisms that prevent such exposure of singularities, preserving causality and determinism on cosmic scales. Binary black hole systems spiral together over millions of years, gradually losing orbital energy to gravitational wave emission. As these cosmic dancers draw closer, their orbital frequency increases and the amplitude of their gravitational wave output grows stronger. In the final moments before merger, they can complete hundreds of orbits per second, while generating space-time distortions that briefly exceed the electromagnetic luminosity of all stars in the observable universe combined. The detection and analysis of gravitational waves has transformed black holes from theoretical constructs into directly observable phenomena. Advanced detectors can measure space-time distortions smaller than 1/10,000th the width of a proton, allowing them to record the signatures of black hole mergers occurring billions of light years away. These observations have confirmed Einstein's predictions about gravitational radiation, while providing unprecedented insights into the population and properties of black holes throughout cosmic history. Active galactic nuclei powered by accreting supermassive black holes can outshine entire galaxies while influencing star formation across vast regions of space. When these cosmic giants feed actively on surrounding matter, the energy released from gravitational potential, energy conversion can exceed the combined output of hundreds of billions of stars. The jets and radiation from these active nuclei can regulate galaxy evolution by heating intergalactic gas and preventing it from cooling and condensing into new generations of stars. Space-time curvature around black holes creates gravitational lensing effects that can magnify and distort the images of background objects. Light rays following curved paths through the warped geometry can create multiple images of distant sources, form Einstein rings, or stretch galaxies into luminous arcs. These lensing phenomena serve both as tests of general relativity and as cosmic telescopes that allow astronomers to study objects that would otherwise be too faint or distant to observe. The relationship between black hole mass and the properties of host galaxies reveals a cosmic symbiosis that operates across billions of years of evolution. The correlations between central black hole masses and galactic bulge properties suggest that galaxy formation and black hole growth are intimately connected processes. Feedback mechanisms allow black holes to regulate their own growth while simultaneously influencing star formation throughout their host galaxies. Primordial black holes spanning enormous ranges of mass could have formed through diverse mechanisms in the early universe. Phase transitions, cosmic string collapse, density fluctuations, and other exotic processes in the primordial cosmos might have created black holes with masses ranging from microscopic scales to many times that of the Sun. These ancient objects could constitute components of dark matter while serving as windows into physical processes that operated in the first moments after the Big Bang. The evaporation of primordial black holes through Hawking radiation could have left subtle imprints in the cosmic microwave background radiation. As these ancient objects disappeared, they would have deposited energy into the surrounding plasma, potentially creating detectable temperature fluctuations in the afterglow of the Big Bang. Future observations searching for these signatures could reveal the existence and properties of black hole populations that vanished billions of years ago. Quantum gravity effects might replace classical singularities with exotic quantum states that avoid the infinities predicted by general relativity. Loop quantum gravity, string theory, and other approaches to unifying quantum mechanics with gravitation suggest that the extreme conditions near black hole centers could trigger quantum geometric effects that halt classical collapse and create finite, albeit highly compressed, states of matter. The complexity of quantum states associated with black hole formation and evaporation continues to grow for exponentially long periods, suggesting that these objects might serve as natural quantum computers, processing information in ways that challenge our understanding of computational complexity. The linear growth of this complexity long after thermal equilibrium is reached hints at hidden quantum mechanical processes operating within black hole interiors. Information theory and black hole physics intersect in profound ways that challenge fundamental assumptions about the nature of quantum mechanics. The apparent destruction of information that falls past event horizons conflicts that with the principle quantum evolution must be reversible. Resolving this paradox may require revolutionary insights into the relationship between information, entropy, and space-time geometry. As we continue our gentle drift through these cosmic mysteries, the profound questions raised by black hole physics remind us of how much remains unknown about the fundamental nature of our universe. These objects exist at the intersection of our most successful theories, yet they persistently reveal paradoxes and puzzles that push us toward new frameworks for understanding reality itself. In the quiet darkness of approaching sleep, the elegant mathematics describing these cosmic giants continues its eternal dance, weaving together space and time, matter and energy, information and entropy in patterns that hint at deeper truths about the architecture of existence. The mysteries of black holes stand as monuments to both human curiosity and cosmic grandeur, reminding us that even our most advanced scientific understanding has only begun to scratch the surface of the profound questions that the universe poses. The gentle gravitational pull of these distant enigmas draws our thoughts inward like matter spiraling slowly past an event horizon, carrying us toward the peaceful darkness where consciousness itself becomes as mysterious as the cosmic phenomena we contemplate. In that approaching silence, the universe continues its ancient story, patient and timeless, full of wonders that will inspire generations yet to come in their endless quest to understand the strange and magnificent reality we inhabit. And so our journey through the cosmic depths draws to its gentle close. We have wandered through regions where gravity becomes so intense that reality itself bends beyond recognition, where time slows to a crawl and space curves into impossible geometries. From stellar graveyards born in the violent collapse of massive stars to supermassive giants that sculpt entire galaxies, we have explored objects that challenge our deepest understanding of existence itself. These gravitational titans continue their silent dance in the darkness between stars, patient guardians of secrets we are only beginning to glimpse. In their warped space-time, information may be preserved or lost forever. Matter spirals inward at the speed of light, and the very fabric of the universe ripples with gravitational waves that carry stories of cosmic collisions across billions of light years. The mysteries we have encountered tonight remind us that even our most sophisticated science has only begun to illuminate the profound questions that black holes pose about the nature of space, time, and reality. Each discovery seems to reveal new puzzles. Each answer opens doors to deeper mysteries. And in this endless quest for understanding, we find both humility and wonder. As your thoughts begin to drift like matter approaching an event horizon, let these cosmic enigmas carry you gently towards sleep. The universe continues its ancient story in the darkness, full of black holes spinning in dimensions we cannot perceive, encoding information on surfaces we cannot see, and connecting distant regions through bridges we can barely imagine. If you have enjoyed this nighttime exploration of cosmic mysteries, feel free to like and subscribe for more journeys to the edge of human knowledge. Until we meet again among the stars, sleep well, knowing that somewhere in the vast cosmic ocean, these magnificent gravitational giants continue their eternal vigil, waiting patiently for future minds to unlock their remaining secrets. Sweet dreams and good night.